Hello everyone. Today we're gonna keep talking about linear classifier. Specifically, we're gonna talk about perception learning, perception algorithm. And we're also gonna talk about the maximum margin classifier. Okay, so let's review what we learned last class. So recall that we want to find the goal is to find a linear classifier. Okay, which has a format f(x). The decision function is equals to f(x) equals to omega, the weight dot product with x. So recall that we want to solve for no intercept. So where the alpha equals to 0 in this case. And once we solve for this weight omega, this vector, we're gonna introduce the way to find the alpha. So let's simplify the problem. So in other words, we want our decision function, our decision boundary cross the origin. So the decision boundary h equals to, remember the decision boundary is all the points on the feature plane such that the decision function equals to 0, right? Equal to 0. So if decision function is positive, we classify that as class C. Otherwise, we do not classify as class C. And what we have here is we have sample points. We have the x1 is a vector or feature, and the xn vector features. You can think of just two-dimension as in your brain. You can just think it's a two-dimensional vector, but in reality, more applications we have general d dimensions, and for each of the data points, we have a training data set. We have label y1. We have the yn. These labels are either positive 1 or negative 1. Positive 1 means this sample point is classified as labeled as in the class C, otherwise not. And we want to find, so the real goal here, find the weight. That can correctly classify all the points. We want to find the omega vector such that, recall that we summarized our constraint problem to be the single condition. So such that we want to find our weight such that the label has the same sign as our decision function. So scalar multiply with this omega dot product with this vector x. We want this to be greater and equals to 0. Which is equivalent to find omega numerically which is a minimizer. Minimize this lost function. So this recall the loss equals to so if our weight can correctly classify the samples, we don't give loss. Otherwise, for those misclassified case, we give a penalty. So that's the idea. Minimize this yi, multiply xi, dot product with omega. Okay. Where this v is just equals to the cases for each given w, the cases that is misclassified, such that the yi and the xi omega has opposite sign. So which means a misclassified case. Misclassified cases. Okay, we give penalty on this. Actually, let's maybe give one simple example. So suppose we have a xy plane. So let's have xy plane. So now suppose we want to we have only 3 data points. Say this point is classified as class in the class. For example, labeled as reliable loaner. Okay, and let's see another one. So the other 2 cases, maybe we have one more case here and one more case here. So those are not in the class C. So those are not reliable borrowers from the bank. So now the question is, how do we find the decision boundary that can cross-classify, that can correctly classify these 3 dots, which is very simple in this case, right? So we are looking for, because the decision boundary is the cross origin. So we need to find the cross origin, a decision boundary. So this is our edge. This could be one of our edge, and this could be our edge, right? This could be our edge. So this perception algorithm tells us how to find the solutions for the set of the solutions where can correctly classify all the cases. Okay. So now actually you can think about it. So this is in the X feature space. This is F feature space. So actually we are looking for the solution omega, so omega space. So since here the omega has the same dimension as features, right? So if your feature has 2 dimensions, our weight is also in 2 dimensions. So you can think this is omega 1, omega 2. Actually, to solve this problem, to solve this minimization problem, the idea is we can find a dual problem, which is equivalent to find omega in omega space. Actually, we have some dual problem. So suppose you have a so you have the X space. you have the omega space. So given you a fixed, so if x belongs to the decision boundary, okay. So in other words, if we have the point x, suppose we have the point x here in the xy feature plane. If this x is on the decision boundary, okay, if this x is on the decision boundary, which means h equals to all the points, if given you a omega, so omega which is perpendicular to this equal to 0. Okay. Actually, this omega also corresponding to a point in the omega space. And this is also equivalent to see the omega such that x is normalized to z equal to 0. So what's this mean? Let's think about the example I just showed you. Let me move this picture below. Okay, so suppose in the xy feature space, okay, so in the xy feature space, again we think this example. So suppose there is a point here in x space. So the question is, what omega vector can correctly classify the points here? Okay. Actually, it corresponding to a point in the xy space. Okay, suppose we have a point here. Okay, and actually all the omegas in this range can correctly classify the points, right? Think about it. If you have a point here, actually all the points on this region can correctly classify this point. For example, if we have a dot omega point here, omega here, so this corresponding to a omega here, and the decision boundary, remember, will be a space that perpendicular to this omega and across the origin. So this decision boundary can correctly classify this point, right? If you have another omega here, maybe let's draw another one. For example, we have an omega pointing here. This is our omega. And we know the decision boundary is perpendicular to this norm omega vector. So, and this point is on the omega side of this decision boundary. So this correctly classifies this point. Okay. So in other words, so summary. In feature space, if we want to enforce the x times omega is greater than or equal to 0, which means, in other words, we want to correctly classify x. Correctly classify x. So what we need to do? So in x space, x should be on the same side of this decision boundary. Decision boundary is z omega dot product with z equal to 0, okay, as omega. Okay, so if we want to correctly classify this point, we need an omega such that so this point should be on the right direction as this side of this decision boundary, and in the omega space, okay, actually, how we can this label this blue region? Actually, we are looking for a point x, so this is corresponding to an x point here, and we are looking for the decision boundary h, such that all w in this region will satisfy that point. Okay, so in other words, omega should be on the same side. On the same side of z given x dot product with z equal to 0. Okay, so this x is a data point, fixed data point. Okay, so keep this in mind. So now we go through every point in our training data set. We can find the solution for omega. Okay, so for example, suppose let's go back to use our simple example with only 3 data points. Okay, so now suppose the one class we have 1 point C here. Okay, this point belongs to class C. And we have another 2 point which is classified as cross. Okay, so this is in the x space. And in another one, we have the omega space. So let's go from 1 point to 1 point. Suppose now we want to correctly classify this point x. So this corresponding to a normal vector in this the x. So this is x here, okay? And what point corresponding to the what's the set of the h omega can correctly classify this point? So actually all the points below this is a decision boundary perpendicular to this x. All the points below this x can correctly classify the points. For example, let me just rewrite this part, redraw this part. I think the idea is very important. Before you even implement the coding, you need to understand why this is true. Okay, so for all the omegas, we find the decision boundary h, and all the points below this below on the same side of this point, this decision boundary will satisfy the points. Okay. Also, okay. Secondly, let's pick about this point. So now let's go through the same procedure for every point. So now for a point, for this point, we have x, right? How do we correctly classify this point? So in the omega space, we need to find a decision boundary which is perpendicular to this x, okay, and across the origin, and all the points, because this is classified the wrong case, right? So and actually all the points on this side should be our solution. Okay. Similar case for this point. So we have another point x here, and we just this is corresponding to a normal vector in the omega space, and we are looking for the decision boundary which is perpendicular to this one and across the origin, and we need to label it on the other side. So which is this case, and we go through every point like this. So the solution will be in this region. So the solution will be in this region. So this all points intersection part is in this lower triangle region. Okay. So this is called the Pythagorean perception theorem algorithm. Okay, that's the idea. And actually in Python you can plot. So this is our this is the plot of our risk function. So this is the plot of risk function. This R omega. Okay, and actually the minimizer for this function, actually if we have only 3 data points, so you can see this is the solution part, solution set. Okay, I will keep talking about this simplest classifier next video.